because we're just going to be talking about resistor combination techniques, which should largely be a review. We're going to talk about why they combine the way that they do, and then I'm going to show you how I do things, just in case you're engineering 120 something, he taught you differently. I am arrogant enough to say that my way is the best because it is. So we are going to use Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law, all that stuff we learned in our last class meeting, in order to figure out how to combine resistors into smaller equivalent circuits today, okay? So just as a quick rehash thing, I'm only going to do Ohm's law up here because I just want to remind you of something. If we have a generic network, that is electrically excited, doesn't matter if it's by a voltage source or a current source, and we measure the voltage drop across the terminals of the network and the current flowing into the network, we can define the resistance of said network as simply the ratio of the voltage divided by the current. So with that in mind, let's look at a network containing resistors in series. So here's my excitation network, just representing some sort of source. Here are my terminals. And then let's say that my network contains some number of resistors connected strictly in series. So I'm going to call this resistor R1, this resistor R2. We're going to be all the way out here to the nth resistor, like so. And I'm going to define the voltage drop across this network of resistors as V, and the current flowing through this network of resistors as I. I am going to define the voltage drop across individual resistors, and I am going to choose my polarity such that the current is going to flow into the positive polarity terminal of every resistor, just so that I don't get a bunch of negative signs all over the damn place that I have to worry about, right? So this will be the voltage drop over resistor R1. This will be the voltage drop over resistor R2, all the way out to VR sub N, which is the voltage drop over resistor R sub N. And applying Kirchhoff's voltage law around this loop, what we'll find is that V, the voltage drop over the combination, is just going to be the sum of the voltage drops across each resistor. So VR1 plus VR2 all the way out to VR sub N, like so. Now I'm going to use Ohm's law to express all of these resistor voltage drops in terms of that current I that's just flowing around this single loop circuit. So that's going to look like I times R1 plus I times R2 all the way out to times R sub N. And we can see that there is a common factor of I. So I can take that out, leaving me with I times R1 plus R2 all the way out to R sub N. And my equivalent resistance is just going to be V divided by I, or R1 plus R2 all the way out to R sub N. So whenever we have resistors in series, we can just simply add the resistor values together. You guys probably already knew that from your previous classes, but we've explained why now using Ohm's law and Kirchhoff's voltage law specifically. A more closed form way to represent this, for those of you that are mathematically inclined, is to use a summation notation, where we're going to let I start at 1 and go to n, and the equivalent resistance is then simply the sum of all of the different R sub i's connected in series. So resistors in series, pretty easy, pretty straightforward. As long as we can identify a series connection, we simply just have to add the damn things together. Okay. So any questions about this guy? All right, so now let's look at resistors in parallel. So same kind of thing here. We're going to electrically excite our network. Now I'm going to have a bunch of resistors connected in parallel as opposed to being connected in series. So this will be R1, R2, and out here will be R sub n. I'm going to define my voltage V here across the terminals of my network. And this current I is the current flowing into my network. So that's what we're going to use Ohm's law to find the equivalent resistance with. And I am going to choose to express my resistor currents in this case. All of them are going to be direction down so that they're flowing into the positive polarity terminal, so that, again, I don't have a bunch of negative signs all over the place that I need to concern myself with. So I'm going to call this current IR1, this current IR2, and this current IRN, like so. Applying Kirchhoff's current law, we can say that the current flowing into the network, I, is equal to the sum of those resistor currents. IR1 plus IR2 all the way out to IRN. Now we can use Ohm's law to express all of those resistor currents in terms of the common voltage V. So this is going to look like V divided by R1 plus V divided by R2 all the way out to V divided by R sub n. And I can factor out V so that I have 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. My equivalent resistance, Req, is then simply going to be the ratio of V to I. So effectively, I'm going to divide both sides through by I, and then divide both sides through by that sum of the reciprocals. And so that's going to give me 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And in a more closed form, this is 1 over the sum from I is equal to 1 to n of 1 over R sub I. So this is how we find the equivalent resistance of a number of resistors that are electrically connected in parallel. We simply sum the reciprocals together and then take the reciprocal of that combination. Now, I'm pretty sure that this is how you guys learned it in your engineering 120 classes, and there's nothing remotely wrong with it, but I am going to wind up using a shorthand notation a whole hell of a lot in this class, and so I want to make sure that you guys understand why I am allowed to do what I'm going to be doing. So let's consider a network where we only have two resistors in parallel, okay? So let's say that I have some terminal A here, and then generically a resistor R1, some terminal B down here, and here we have a resistor R2. And we're trying to find the equivalent resistance seen between these terminals, which I'm going to label as RAB. Okay? That's the notation we're going to wind up using a lot in this class, so I'm just introducing it now. So we just learned that RAB should be equal to 1 divided by 1 over R1 plus 1 over R2. That is absolutely correct. And if we wanted to, we could leave it like this all day. But I can make it a little easier for us to do by just playing around with some math, right? So I'm going to multiply 1 over R1 times R2 over R2. And I'm going to multiply 1 over R2 by R1 over R1. So I'm not doing anything illegal here. I'm just multiplying by fancy representations of the number 1, right? What that's going to give me is 1 over. So I'm going to have R2 divided by R1, R2 plus R1 divided by R1, R2. So now I have a common denominator in my denominator, which means I can just straight up add those two together, right? So that's going to look like 1 over R1 plus R2 divided by R1 times R2. And since I have 1 over that fraction, that I can just say that the whole thing is just the reciprocals, or R1 times R2 over R1 plus R2. This is how you're going to see me combine resistors a whole hell of a lot in this class, particularly when we have 2, but we can apply it for more, and we'll talk about that later, right? So instead of having to go through the pain in the ass that is 1 over the resistor plus 1 over the resistor, I can just say multiply them and then add them and take that ratio and be done, right? So, excuse me. If we had a network like this, so let's put a 6 ohm resistor here and a 12 ohm resistor here. We could very easily see that the equivalent resistance is going to be 6 ohms times 12 ohms over 6 ohms plus 12 ohms. So 6 times 12 is 72. 6 plus 12 is 18. 72 over 18 is 4 ohms. Call it a day without having to worry about all those reciprocals and all that kind of crap. Now, just as a quick thing here, let's do 10, 20, and 50. This probably isn't going to come out cleanly, but it'll be okay. So now we have 3 resistors connected in parallel. Okay. So some of you may be thinking that this would simply be 10 ohms times 20 ohms times 50 ohms divided by 10 ohms plus 20 ohms plus 50 ohms. Why is this not true? glaringly obvious that messes this up. What are the units of the numerator? Ohms cubed. What are the units of the denominator? Ohms. Is ohms cubed over ohms give you ohms? No. So this does not work, right? We can't do it like this. Instead, what we would have to do is combine two of those resistors into a single equivalent resistance and then apply that technique a second time in order to handle three resistors, okay? So instead, we would say, well, 10 in parallel with 20 is going to look like 200 over 30. Actually, I'll just redraw this below it so we don't lose the original thing. So what I'm suggesting is that we combine the 10 and the 20 in parallel into something here. So 10 times 20 is 200. 10 plus 20 is 30. So I'm just going to leave it as that, even though it could obviously be simplified to 20 over 3. Now I have my 50. And so the equivalent resistance will be 200 over 30 ohms times 50 ohms over 200 over 30 ohms. Sorry, that ohm shouldn't be in the denominator. Plus 50 ohms. So all I'm trying to illustrate here is that if you use this shortcut method, you have to pay attention because technically speaking, it can only be used for combinations of two resistors, but we can just lump two resistors together and then use that equivalent resistance to lump two more resistors together and so on and so forth if we didn't want to have to use the big reciprocal thing. Realistically, after I hit like 4 resistors, I'm just going to use the reciprocals because it's less math. Yes. Do what now? So if we were to try to do this in one go, I think I follow what you're saying, but I'm old and I couldn't quite hear things. So what you would have would be 10 times 20 over 10 plus 20. This combination would be multiplied by 50. And then you'd have 10 times 20 over 10 plus 20 plus 50. If you wanted to do it in one fell swoop. So I don't think we're ever going to get to a real situation to where, let's see. Just for shits and giggles here, and this is just me playing around with algebra, not anything particularly important. I could multiply the numerator and the denominator by 10 plus 20 over 10 plus 20 to clear those fractions. And so that would be 10 ohms times 20 ohms times 50 ohms and then that would be 10 ohms times 20 ohms plus 50 ohms times 10 ohms plus 20 ohms. I don't know that that's prettier. Like mathematically, that's what how the algebra leads me. But I don't know that that's any more simple than just using the reciprocals from the jump, something like that. Yeah. No, I'm misunderstanding you. Do you want to come up here and show me what you're talking about? Or do you want to do it on the board so it's not recorded in perpetuity? Or do you want to talk about it? Okay, I'm not trying to embarrass you. I'm just not understanding what you're saying. If it works for you, that's great. I'll talk to you after class and we'll try to sort through it. Yeah, I don't want to put you on Front Street in front of everybody. All right. So these are our resistor combination techniques, or this is how we're going to combine resistors in series and resistors in parallel. Now let's actually apply this to a network to where things aren't super obvious, okay? So once again, I'm going to look at one of your web work problems, and we're just going to go through some stuff. So let's look at homework set number 3, and I think problem 2 would be a good one. Yeah, this is a good one. So this is fairly ugly looking. Ashton's making a terrible face. So I'm not going to bother with the numbers that are used here because your numbers are going to be different and all that kind of jazz. We're just going to throw some numbers in and take a crack at things. Okay. So we're going to look at a network that looks something like this. Bless you. Let's just call this 10, 20, 30, 40, 50, 60, 70, 80, and 90. I'm going to use the same terminals as are in the web work. So this is going to be terminal C, B, A. Down here is D. And as part of the homework problem, we were asked to effectively solve this for 3 different equivalent resistances. And depending on which set of terminals we look into, we're going to get different resistances. So I don't bite myself in the ass and come up with something where I need to use a delta Y transformation, which we're not going to talk about in this class. I'm going to choose to do one of these 3 sets of terminals. So you guys get to tell me whether you want us to find the equivalent resistance between terminals A and D, B and C, or C and D. Camden, pick. C and D. Okay. So our goal is to find R, D, D. So the first thing that I'm going to do is I'm going to identify all of my nodes in this network. So I'm going to start here at the top left. This guy right here is node C because we already have a terminal labeled as C. This guy right here is going to be node B. This guy over here will be A. Nope. This guy here will be D. And then we have 2 other nodes left that don't currently have a letter. So we'll have to give them letters here in just a moment. So let's call this guy E and this guy F. All right, so pretty obviously we have 6 nodes in this network. And we're trying to find the resistance between nodes C and D. So what I'm going to do is I'm going to put node C way over here on the left and node D way over here on the right, and I'm effectively just going to play connect the dots or connected nodes with resistors, okay? So what's the easiest way for me to get from node C to node D? The 30 ohm resistor, because it's connected directly between nodes C and D, okay? So I'm going to start with that easy path first. I'm going to put a check mark by it to remind me that I've already taken care of this path. All right. So what's the next easiest way that I can get from node C to node D? I think it's going through node E, okay? So I'm going to put node E here in the middle, and I can go from C to E through the 10 ohm resistor. And then I go from E to D through the 20 ohm resistor. So I've taken this guy into account and this guy into account. All right. What's a different way that I can go from C to D? C to B to D, okay. So let's put B right here. To go from C to B is through the 40 ohm resistor. And to go from B to D, the easiest path is through the 50 ohm resistor. Now, I've got several different ways that I can go from B to D. So now I'm going to work my way through those paths, right? So the easiest way that's remaining would go from B to A to D. So I'm going to put A right here. So from B to A is going to be the 60 ohm resistor. And then from A to D would be the 70 ohm resistor. So we took care of this guy and this guy. But now I can see that there's also a path that leads me from A to D that isn't the 70 ohm resistor, and that goes through F. So I'm going to put F down here. I go from A to F, and then from F to D like so. So A to F is the 80 ohm resistor, and F to D is the 90 ohm resistor. So now I have this thing drawn in a way that I can just analyze it from bottom to top in order to find an equivalent resistance. And it should be very easy to see which things are connected in series and which things are connected in parallel, right? So 80 and 90 are very obviously connected in series because there's only one point of interconnection, no branching paths. So I can replace the 80 and 90 with a 170 ohm resistor. Now, the 70 and the 170 are obviously in parallel. So I'm going to use that combining two resistors trick. So 70 times 170 divided by 70 plus 170. I get 49.583 and some change. That is very obviously in series with the 60. So combining them, I get 109.583. That is now in parallel with the 50. So answer times 50 over answer plus 50 we get 34.334. That is in series with a 40 ohm resistor. So that's going to look like 74.334. And there's not really any simplifications that I can make on this bottom bit now, so I'm going to move up to the next tier where I can see 10 is in series with 20. So that's very obviously going to just look like 30 ohms. And here I would probably either do one of two things. I would just do the reciprocal 1 over 30 plus 1 over 30 plus 1 over 74.334, take the reciprocal of that. Or because it happens to be 30 in parallel with 30, I know that's going to be 15 very easily. So I might combine those and then do the 2 resistor trick. But at this point, it's very easy to see that we just have a simple network of resistors in parallel, and we can treat it however we want to treat it to get the equivalent resistance. So that's the process that I utilize to make ugly, terrifying looking things more simple in order for us to analyze it.